here, like the tracks going around the lab. So like this half of the lab is pretty much for ambulation testing our devices. And then on this side, of course, you have desks for everyone. We don't have cubicles, we like to have pretty open space, and everything's on wheels, so we can change and reconfigure the space depending on the experiment that we're running. We have a little bit of the kitchen over here, and some 3D printing over here. And then on the other side of the lab as well, if you want to do that, we have benches, some tools for rapid prototyping. Although most of the machining, it's really the outsourced. Okay, so if you want to come this way, on the corner, this corner.
Doing some smooth walking.
Smooth walking?
Yeah.
Okay. So you probably already the work that we do related to prosthetics and conditioning, particularly we're focusing on novel technologies for people with above knee amputation, which means like any both knee and ankle foot prosthesis modules. And so these are some of the devices that we've developed. This one is Frankie over here. It's probably the first prototype that we built, which you can probably tell. And this is hard to tell, but this is like a backpack you have to wear, and it's all tethered, and really only one joint is powered. And then after that, we developed Romeo and Juliet. So this time we have both a power knee module on top and a power ankle module over here. And all the electronics is on board. It's not super small, but everything is on board and battery powered. So we are not tethered anymore with this device. And what makes this device unique, and what makes pretty much all our devices unique, is they're very, very lightweight and still able to provide enough torque and speed to support major ambulation activities. And so this device here was developed around 2017, 2018. We've been using it a lot over the years, but now me and actually Lucas have developed a new device. Maybe me will show you a little bit.
Hi everyone, let me show you the last 3 years of my PhD. So this is the next generation of the prosthesis that we have in the lab. We kind of learned a lot from the second generation, and we want another generation that can be used as a take-home device for amputees. And with that in mind, we make things even smaller and lighter and more robust. We have to rethink everything, not from scratch, but almost. So when we design a new device, we always start with something like this, modeling. So we built a very detailed model of the leg. It can see like linkage, motor, and transmission, and everything. And we optimized them all together to meet the required weight and size that we want. This can easily take a year, and it did. But after that, this is the fun part. You go into SolidWorks and you make beautiful stuff. You can see here, the outer structure is very refined. Most likely because we need to optimize for weight and size as well, but we also want to make it beautiful because people put it on here. And this is a 3D printed version of the final prototype. This is officially version 15. So after we design something, we always print and check if everything's all right. After that, we send it out for machining. And we come up with a beautiful prototype like this. This is the knee and ankle module exposed. The ankle has exposed, which is very cool. We actually have a leg built and assembled, which my friend Lucas will show you right now.
Yeah, let me go.
Yeah, you go first.
All right, let's go this way. All right, it's confirmed. So the one you saw over there is on the bench, and we set it all up because we're still working on the embedded electronics. There's some programming, some benchtop testing, making sure that everything works as expected. But then once we are done with our benchtop testing, what we do is that first we test on us. So we put the leg on a bypass orthosis, which is something that looks like this. The leg is stretchable there, as you can see. So we can sort of pretend that we have an amputation and try and test the eye level controllers like for walking, and stairs, and ramps, and so on. So I'll give you Lucas and Sarah so they can show you over there. You want to show the controls?
Oh, sure. So here's what our control panel looks like. We have different tasks over here so that we can test each of the different activities in their own space. So if someone's working on walking and trying different methods of walking, we can have different control settings there. These plots here kind of let us see in real time what is happening with the leg. So we've got the joint positions for the knee and the ankle, as well as the joint torques for the knee and the ankle. And then this is our custom GRF sensor that gives us a force and torque at like right above the ankle.
And so just so you know, so everything is running on the embedded electronics that we built for the knee and ankle, but we use Wi-Fi to communicate to the laptop computer so we can change the controllers, we can kind of see what's going on with the leg online as it happens and make changes that we want. Okay, so. All right, good luck.
So I'll give a little demo here. This is kind of how we do our testing of different control algorithms that we come up with. Is we'll come over here, we'll put the leg on, and then we'll just try out the controller before we put it on a subject, just to make sure that it works out. So here's walking, and we can walk.
So we have a question asking whether we have any plans to develop a machine learning based controller.
Joe's working on it. I don't know where.
Joel
I'm working on one.
Joel is working on one.
Yes.
Yes.
Using sonomography to read the muscle contractions, and then through those muscle contractions, they'll determine how the knee flexes. But that's further down the line. Right now, we're still doing preliminary studies.
Yeah, so it's absolutely in the works, and that'll
So we
be
wanted to use it as minimum machine learning as possible, because we think that a lot of what happens with the human leg and in ambulation is actually not controlled, but the result of the intrinsic dynamics of the leg and intrinsic behavior and properties of the leg. And so we care a lot about making the system so lightweight and so efficient that can pretty much freely swing and walk. And then on top of that, we try to provide the user with as much control and agency, I guess, possible on the leg. And so we're working on electromyography controller, like neural-based controller. Grace, you're working on one of them. I don't know if you want to talk about it or not, but we think that the machine learning part really has to come after these building blocks are set in place, because otherwise it will hinder us from understanding what is actually happening with the leg and what we have to improve.
sweet. Does that answer your question? You feel free to ask a follow-up question if not. But in the meantime, pretty cool.
So now we also work on stairs. Of course, that's a big thing for folks with above knee amputations, because currently they have to walk upstairs with a passive device just like this. And so it's a big difference for them to be able to go to walking up in a gait pattern, more step over step. So with this device, you can go step over step, and that's a big activity for folks with above knee amputations that this enables them to do.
Woo! All right.
Okay, so we're gonna move on to the time, so maybe let's just go around this way. So one thing that we started doing a little bit more recently is taking all the things that we had learned and developed smaller prosthesis and starting to put them into exoskeletons. So here we have one of the prototypes we developed. Sergey worked on this when he was an undergrad and now is a graduate student in my lab. And this big guy over here is Jack White, one of the smartest person in his lab. And so what makes this device unique again is that everything that you see here is custom made. The actuation system, mechanics, and the electronics. So this is kind of hard to tell because of the backpack over there. And again, what we do initially is just focusing on design and control Then as soon as that is ready, we started testing the specific population. And Andy is actually working on stroke subjects and looking at how the knee exoskeleton can help someone who has hemiparesis to stand up more symmetrically and kind of make it easier for them to stand up. And one of the devices we developed, this one that Dante and Marshall are showing up here. This is a hip exoskeleton, which means that it provides assistance for your leg as you're walking, flexion and extension, so back and forth. And again, everything you see is custom. And what's really neat about this one is it's very small and lightweight. So this is a carbon fiber tube that we just bought, and it's hard to tell, but inside of this carbon fiber tube, there's a DC motor, and there's sensors, gears, ball screw, actuation, everything that is necessary for this device to provide assistance in flexion and extension. And not only the mechanics of the electronic we custom made, we also do our own electronics. So this is the electronic board we've developed to control the exoskeleton, which sits kind of on the back. And it's based on the PIC 32, so it's all embedded electronic. We have the option to plug in a Raspberry Pi module, which give us access with Wi-Fi, give us access to data monitoring and changing the parameters online as we like it. So, and then finally, the other thing I kind of want to point out here, maybe not to talk more about that, but is also the ergonomics and the interfaces are custom made by us. And I don't know, Dante, you want to say something about this new model?
So we spent a lot of time working on this. We wanted to make it very lightweight, but still be comfortable. And lightweight was important because when you walk wearing it, it takes effort to carry it around with you. And we want to minimize that additional effort. But with making it lightweight, it still needs to be stiff. And so if you have a really flimsy interface, something that might be just made of fabric, then when you put a lot of torque through it, the interface starts moving, and that isn't transferred to the individual, doesn't help them move their legs or their hips. So we connected the two sort of compliant sides with this rigid bar, and that means that sort of acts like an anti-roll bar, and it resists independent motion of the two sides. And then furthermore, this pad here also will sit on your lower back, maybe sort of in like the lumbar region, and that helps also resist sort of forward motion, and makes the whole interface, the combined interface, and human pelvis interface connection very rigid and stiff. And then I guess the last thing I'd point here is we have our embedded batteries as well. So the battery pack and the electronics are kind of built into the frame to help with ergonomics.
This is just one thing, like one thing that is super neat about this one is that this is actually carbon fiber, 3D printed carbon fiber, which it's like a special 3D printer we bought last year. And it's super interesting because it makes things very lightweight and gives the flexibility of 3D printing. But because there's carbon fiber, they're actually as stiff as making them in metal, aluminum. So I don't know, Mark, if you want to just show the device. And
yeah, so I'm just gonna do some overground walking with the exoskeleton.
Oh, sorry guys, I'm walking into stuff.
So right now the exoskeleton is assisting me as I swing my leg forward and then as I extend my leg backward. And it senses how fast and slow I'm walking and provides assistance at the corresponding times based on my walking cadence. So.
Awesome. We are just moving to TV really quick. Joy made a little announcement that there's not anything scheduled right after this, so we're gonna go over a couple minutes, but if anybody has like a, you can always dip out if you need to. And after this, like little demo right here with Joel, we can take some questions for a few minutes.
Okay, so once we develop all these devices, the mechanics, the electronics, the controls, the benchtop testing, develop the algorithms, what we do is that we put it on people to see if they actually work and make their mobility better. And so we also have to then assess if that can happen. So we work a lot in mechanics, I guess, area, feel that some things that we use are like this motion capture based system, ANU-based motion capture system. This is from Accents. And so what it does is that it gives online application of the kinematics. So that's actually Joel bending his knees, and if he walks around, he Yeah, then you still leave them there moving around. And the bottom data, the bottom tells us about the joint movement. So flexion, adduction, for example, and flexion extension of the other side of the knee and ankle. And so the idea is that by looking at the biomechanics, we can actually assess the effect that the assistance of the device is having on ambulation. And,
I'll get a few shots of Joel and little Joel. Big Joel and little Joel showing off our accents.
And so the access is really nice because we can walk around the lab. So here in the ambulation suite, the ramps everywhere. We're even like in the staircase outside and use a recording of the kinematics. But at the same time, it's not the most accurate system that one can use for motion analysis. And so sometimes what we do is we work with the physical therapy department and the kinesiology department to do motion capture, like camera-based motion capture. And we work with different people right there, but our main collaborator is Bo Foreman, who's the director of the motion analysis lab over there. So perhaps Sarah and Andy can show a little bit of how that is different.
They have some.
Yeah, so this is a great tool that we use in the lab because it's like very mobile and very quick in processing time. And then another alternative that we have, which has a lot more accuracy, is motion capture. So all of those dots are reflective markers that we have placed on the participant in our study. And then in real time, we can actually watch them walking with all of these colors connected to show the different segments, to show where their knee joints are. And in post-processing, we kind of look at the data, make sure that all of the markers are being seen and properly labeled. And this allows us to more accurately analyze like their joint movements, their joint efforts, looking at forces and torques through the ankle and the knee and the hip. We can also record EMGs as well. So we have a Prosthesis system for EMGs. So these little guys actually can be placed on their muscles. And then we can see these signals within Vicon itself. So here is an EMG signal from
The soleus.
while the individual is walking. And so every step you can see the muscle effort on top of we're already collecting their joint movement and their joint effort as well. And so this is one of the many tools in which we use to kind of understand how these devices that we're building and designing, how are these devices helping the user? How are they interacting with the user? And from there, how can we improve them and make them better?
Thanks, everybody, for watching. Does anyone have questions that we can?
Take any questions, and we don't have time for the screen, so.
Are you hiring any students for the fall? And if yes, which project are you recruiting for?
We are in many students for the fall. We'll see how many, 2, 3, or 4 to be defined. We have projects ranging a little bit everything. We need more people working on the biomechanics. And although, it's not really only on the biomechanics, really is working more on testing the devices that are being developed already on subjects. So either testing amputees, testing stroke subjects, or other populations we're interested in future, also like children, for example, cerebral palsy. And so that kind of work is more related to like high-level control, human-robot interaction, and then biomechanics for assessment of ultimately of the performance of the device with the user. And also we are hiring on design. We just got a new grant from NSF, which is about designing new high-performance exoskeletons. This is about to start. It's actually going to start in a month, and it's going to run for 5 years. So that's going to also cover full duration of a PhD, which is pretty unique. It's not easy to find someone having already the money for the old duration PhD as a research assistant. And we also need more people on the power prosthetics project. We got another grant from the Department of Defense, and we're going to send our power leg home with a few subjects, which has never been done before. And so we're really, really excited about being able to be the first to do that. And we need people both working on improving on the current design and improving on current controllers for that specific project.
There was a question that said, new what for exoskeletons? And I'll answer that. He said a new NSF grant, so National Science Foundation grant to build new exoskeletons.
Yeah.
It was just a clarification.
Yeah.
Okay, any other questions that anybody has?
How's the lateral stability on your exoskeleton joint? Because I noticed you're using kind of like the handrails to like help stay balanced. Do you have like
Do you mean on the
stability in that direction?
prosthesis? Do you mean on the prosthesis or on the exoskeleton?
On either.
So the balancing on the prosthesis is actually a lot harder for us than for people in amputation, because the bypass device, the orthosis that we stick to our leg, is not very stable. And also when you go on stairs, you're actually hitting your foot, which is kind of bent 90 degrees on the back. You hit the foot on the steps. So it's actually really, really hard to bypass. And there are videos online of amputee subjects walking over it. You can see they can do really well. We actually go outside the lab to test. We've been around campus as well. For the exoskeletons, right now, the lateral stabilization is positive. So you can move your hip sideways like this, but it's not assisted. And so Dante is actually designing a new generation of the hip exoskeleton that is going to have power abduction, which means like this movement here is going to be powered, abduction, and also this movement in this direction is going to be powered. And so the advantage of having that is that you can control your foot placement. So based on how you control your foot placement, you improve lateral stability. And you can also apply perturbations of force when you're walking so that you can stabilize a person if they were to receive a perturbation.
So there's another question. Are there any interest in building exoskeletons beyond the lower limb, for example, back support?
Yeah, definitely. I mean, we're interested in expanding our research. We are at the stage where we have more ideas than actual people that can do that. So right now we're just limited by the number of people that we have that can do the work. There are 9 PhD students, 8 PhD students, and 2 master students currently. Postdoc starting soon, and recruiting more grad students. So definitely interested in expanding on that as well. But we also want to make sure that we don't just build things, but we also test them, and we also do the next step of making sure that they work with people, that people like them, and that it can actually help them. So we don't want to start new projects and sacrificing the ones that we still need to complete.
Let me see what time it is. Okay, so it's only 1:26. Does anybody have any other questions? Probably take like 2 more, maybe. What do you think, Joy? So I hope that's okay.
Yeah, probably.
Are you looking to bring in any master students this year?
Depends. I mean, I'm always open to looking for master students. My preference is always for PhD students, because projects that we have, like 5-year-long projects, 4-year-long projects, 5-year again, the NIH projects. So in order to allow continuity of the projects, people we hire PhD students. Every now and then we'll have master students, but to be honest, it's mostly because I see the potential of someone moving to PhD at some point, and so they start as master. In fact, both Joel and Lucas started as master students, and then they decided to stay for PhD. Best decision ever, Joel, right?
Joel says yes. Good.
Best decision ever.
Okay.
What are some advantages of removing the need of user like deciding how the leg moves, that like rather than the other type?
Can you repeat that? Sorry.
What are some advantages of like removing the need for user decide how the leg moves, that leg moves on its own, like automatically?
So the user is defining the movement a lot of times. So we're not like letting the leg have full control. We're letting the user control the leg is what our research is aiming at.
So there's a fine line, right? So the interesting thing about ambulation and lower limb motion in general assisted devices is that when you walk, you don't really think about, oh, bend my knee, push with my ankle, move my hips out. You just think walk. Just think walk. Maybe you think like start and stop walking. Maybe you think about walk slower and faster, turning. But you don't really think about the joint movements in the same way you think about it in the upper knee. And so there's some level of subconscious or even reflex pathways that play into the movements that are generated during ambulation. And so the part of the autonomous control that we are implementing are meant to replace those unconscious synchronization that you have in the lower limb. And then at the same time, we also hoping to give users eye-level control of what they want to do. And so doing that is really tricky. It's not easy. And so a lot of things that we're doing are related to using the movements of their residual limb in order to infer what the movement should be, and then using neuro commands, so the activation of their muscles, the construction of the muscles inside their residual limb, inside the socket, to decide how much assistance, for example, the leg is providing. But it's a very new field. Like, you have to think that there are only in the world, there are only 5 devices that are powering knee and ankle, and there are only 3 devices ever in the history of humanity that have demonstrated ability to do stairs and sit-to-stand. One is ours, one is in Chicago, one is a Vanderbilt. Chicago, Michigan, it's the same leg, and one is a Vanderbilt. But what makes our leg unique is that it weighs half of any other device. It still can provide the same torque power. And so by being so lightweight, we can do a lot of activities that other legs cannot do.
Awesome. So there's
Thank you
another
very much.
there's another question. Are you interested in getting a bachelor's student for a PhD? I think versus a master's student is probably.
I think most of the people have started here, they're coming without master. That has been like traditionally what we've done, but I don't really have a preference necessarily. I think it's mostly about finding the right people that are a good fit for our mission and also are a good fit for our lab environment. We are a very collaborative environment. Everything is based on teamwork, and we want to preserve this mindset that we have. And so it's not really, to be honest with you, it's not really about how much you've learned during your undergrad, but it's about your potential to learn even more while you're here as a PhD student. That makes a huge difference in the selection process. So coming with a master, coming without a master doesn't really makes any difference.